No, that doesn't make no dang sense. This is not, that looks like an endothermic reaction, not an exo. Dang it, Alex.
That reaction 1 is an exothermic reaction. The first reaction that you had there. Or sorry, did I say exo? That reaction is an endothermic reaction because the products are higher in energy than the reactants. The first reaction there. But you unshared your screen, so I can't see anymore.
Oh, sorry. Products.
So that one right there, that's an endothermic reaction, the one that you're mousing at right now.
Yeah, and it's saying that reaction 1 is somehow exothermic because it says, what? Oh my God, my dyslexia is kicking my butt today.
It happens.
Hi, Dr. Musk.
Hello.
How are you?
I'm doing okay.
How's the house stuff? Is it going all right? You back hurt?
Yeah, everything hurts. Yeah. 40s ain't the 30s, ain't the 20s. So yeah, everything hurts, but it's good. We're doing some work on the subfloors right now, and then we're going to be putting in fresh plywood on top of those, and then putting in our new floors, which is going to be really cute. And
that sounds super cute.
Yeah, a decidedly mid-century modern concept. So lots of copper fixtures in the house and things that look
What's great about that is that they'll keep themselves clean, so you don't have to pay for like Clorox wipes.
Yep. Intentionally dated, I think, is like the vibe that we're going for. So it's going to be pretty.
So is it going to be like steampunky or like dated to, what was it you said?
Like imagine grandma's house from the 60s, but with like modern amenities instead.
Oh, okay, okay.
Yeah.
Hey, Sarah. Welcome to class.
Oh my gosh, it's been a day.
Yeah, tell me about it. This is like my third meeting today.
You had what?
This is like my third meeting today.
Oh, this is like my 8th.
That's a few.
Yeah. That, and I'm living out of boxes, which I know Dr. Musk you can relate to right now.
Also living out of boxes. Yeah. Actually living out of remnants at the old place. And most of the things that we use occasionally are already over in the garages at the new place. We can't actually move into the house yet because there's so much renovation work left to be done. So we probably have at least 2 more weeks worth of hard work before we can actually start moving into the house and using that space. So
yeah, we're still going back and forth from Oak Harbor to Kirkland a couple times a week.
I don't even know where Kirkland is. Oops.
It's an hour and a half away.
That's probably why I don't know where it is. That's a long way away.
Yeah, it's south, an hour and a half south.
We also have been having trouble procuring lumber for our projects because lumber is very scarce right now.
I heard that.
Yeah, we won a couple of bidding auctions for like recycled plywood and lumber, and hopefully that's going to be enough to finish our house off.
Yeah, so. I think, yeah, the only thing I pretty much have set up is like my home office. So I have like this little alcove in the living room. So like my office is set up and that's it. And then like there's like a little spot on the couch where like my husband and I can sit and that's it.
Yeah.
Everything else, oh, and the bed, but everything else is like boxes everywhere.
All right.
So just so you know, I'm behind on everything.
Okay. How much of chapter 6 do you still have left to get done? If you, I mean, you don't have to say, but
I haven't started. I'll just be honest.
Okay, that's a lot. You know, yeah. It is possible.
I've got half of it done.
It is possible to email your professor and ask for an extension.
I know. I didn't. I know. I haven't done that yet because I've been like so busy at work that I haven't had opportunity to.
But I'm just saying, if you need a couple of extra days to get it done, with the chapter 7 is our last chapter, and the 18th is our last day of class. So we have some days left before our final exam. So if you need a couple of extra days to get the chapter 6 Alex done, then that's okay. And I have been getting a number of people coming by office hours for Le Chatelier's principle, for other stuff from chapter 6. So I'll look and see where people are at with Alex after class today as a class. And if everybody could use a couple more days, then I don't mind just like extending.
I just have one more thing to do on Alex. For
Lucky
topic
you.
6.
Sorry, don't mean to be petty, but
That's like the only. That feels like the only good thing that happened to me today.
oh
Yeah,
really?
Julie,
That
don't
kind of
take
day?
away the only good thing that happened to her today. That's
Wait,
not fair.
that's the only that's how your day's been going? My bad. I take it back. I'm sorry.
Okay.
It's
That's
been
good.
that kind of day for everybody.
Yeah, we want to support one another. Congratulations, Olivia. I'm so glad that you've gotten almost all the chapter 6 Alex done.
Me too.
That's amazing.
Yay, Olivia.
Congratulations. I'm sorry. I can't say that on the recording because we have sensitive ears.
Yeah.
Not nice person.
No, you're a nice person. We just forget that we're nice sometimes.
Just rules. Just take out the sarcastic tone.
I'm here.
Okay, so let's do a little bit more practice. We will do 3 quick practice problems with Le Chatelier's principle. And because there isn't one directly in Alex about pressure changes, we'll look at this one together to talk about pressure changes, and then one more also. All right?
Wait, can I actually ask a question?
Yeah.
I was doing Alex and it was in chapter 6. For some reason, all of the catalyzed reactions always had less activation energy than the uncatalyzed reactions.
That's right. That is the definition of a catalyzed reaction. Catalysts work by making activation energy lower. So you should expect that in any reaction that has a catalyst, the activation energy is going to be lower than the reaction without the catalyst. Now, everything else about the reaction should be the same because you have the same reactants and the same products, right? So wherever let's use our words carefully, wherever the reactants are in terms of energy, they're going to stay there with or without a catalyst.
Yeah, that made sure the levels lined up.
There. But the size of the hump in the middle does change with a catalyst. The hump gets smaller.
So it's actually within the definition of what it means to be a catalyzed reaction.
Yes, absolutely.
Okay. I didn't read the explanation. I just kind of guessed and got it all right.
That's what catalysts do. They lower activation energy.
Okay.
The how that works is like multiple semesters of graduate level coursework, but that's what
I'm not looking for the how. I'm just trying to make
the how
sure
is
that I'm
really
not
hard.
like
The what is pretty easy. They lower activation energy.
Yeah.
Okay. So let's read through this one together. Nitrogen and oxygen react to form nitrogen monoxide. And we can see the balanced chemical equation there. The reaction is endothermic. Suppose we have a mixture of those 3 gases at equilibrium in a closed reaction vessel. Predict what change, if any, the perturbations in the table below will cause in the composition of the mixture in the vessel. Also decide whether the equilibrium shifts to the right or to the left. Okay? So I'm going to suggest that when we think through Le Chatelier's principle, I want you to answer the second part instead of the first part. Let's figure out which direction the reaction is going to shift first, and then figure out what happens to the pressure of O2 or the pressure of NO. All right? So if we raise the temperature, is that going to shift our equilibrium to the left or to the right, or not at all? Now, if you know the answer and you're firm about it, just keep it to yourself for a second so people have a chance to think through, all right? So Le Chatelier's principle tells us that whatever we do to disturb the equilibrium, the reaction is going to counteract that. So if we raise the temperature, the reaction is going to respond by trying to lower the temperature. So the question we should be asking ourselves is, how can this reaction lower its own temperature? Now remember, this is an endothermic reaction, and Jennifer has correctly written down that that means that heat is a reactant in this reaction, right? We have to put energy in, heat energy in, to make this reaction work. So let's think about what that means if we make more products or if we make more reactants. If we make more reactants, if the reaction goes to the left, that's going to make our temperature go up because we're making more heat. So if this reaction wants to have its temperature go down, the way that it could do that is by making more products, right? Making more heat would cause the temperature to go up, and that's what we would do if we're making more reactants. Using up heat would make the temperature go down, and that's what we're going to do if we make more products. So the equilibrium should shift to the right here to get rid of the extra heat. If the temperature is lowered, then that means the equilibrium, if we lower the temperature to disturb the equilibrium, Le Chatelier's principle says the reaction is going to try and raise the temperature, counteract what we did to disturb the equilibrium. So this reaction can raise its temperature by shifting to the left to make more heat to replace the heat that we took out when we lowered the temperature. Okay, so now we know which direction each of these is going to shift the equilibrium. What happens to the pressure of O2 if this reaction is shifted to the right? The pressure of O2 is another way of talking about like how much O2 is going to be around, because the more O2 we have, the more pressure of O2. If this reaction shifts to the right, are we going to have more O2 around, or are we going to have less O2 around?
More.
More, so O2 is a product here, so when we make more products, we make more O2?
No, we made more NO.
We're making more NO, but Luz, where does the NO come from?
Wouldn't it be no change because O2 is a reactant?
Well, both the reactants and the products change when the equilibrium shifts. Because remember, the equilibrium shifting, the reaction shifting, is either going to get rid of some reactants or make more reactants, or it's going to get rid of some products or make more products. One of those
decrease, wouldn't it?
Yeah, if we're making more products, the only way we can make more products is to get rid of some of our reactants. That's where the products are coming from, is they're coming from us getting rid of some of the reactants. So if we shift this reaction to the right to make more NO, at the same time, we're going to be using up O2. We're going to be getting rid of some O2, which means that the pressure of O2 should be going down, right? We're getting rid of O2 because we're shifting to the right to make more products. And if we're making more products, we're using up, we're getting rid of some reactants. Now, if this reaction shifts to the left, like it does in the second case here, what's going to happen to the pressure of NO? If the reaction's shifting to the left, that means we're making more reactants here. So if we're making more reactants, what happens to our amount of NO?
Goes up.
No, goes
Is
down.
NO a reactant?
No, sorry, I lied. It's going down.
There's only two options here, right? It's either going up or going down.
I was
But we
testing
wanna be
everybody
clear
to see if
about
they were paying
why
attention.
it does what it does. All right. So if the reaction shifts to the left, if we're making more reactants, that's what shifting to the left means. Then the only way that we make more reactants is by getting rid of some NO. Our NO has to decrease because that's where our N2 and our O2 are coming from, right? If we shift to the left side to make more of these two, then this has to go down at the same time. So if N2 and O2 are going up because we shift to the left, if we're making more N2 and O2, we have to have less NO around because of that, right? That's where the N2 and O2 are coming from, is by using up that NO. So our pressure of NO should go down here. All right, let's look at a concentration example. That's that famous reaction, the Haber process that we were talking about yesterday. So do yourself a favor, and for each one of these two perturbations, talk through Le Chatelier's principle. So the disturbance, the perturbation is, we're taking some H2 out of the reaction. So if we're taking H2 out, Le Chatelier's principle says the reaction's going to try to do what?
Put it back in.
Yeah, put it back in. In other words, make more H2. If we take some H2 away, the reaction's going to try and make more H2. So which direction does this reaction have to shift to make more H2?
Left to the left.
That's right. Everything you own in a box to the left. That seems very fitting this week for me.
Well, that's about her kicking someone out.
I know, so it's not a
Like,
perfect
it's not a
analogy
movie.
yet, so we don't read too much into that. My wife and I are fine.
It's good to know.
Okay, so what about for this second perturbation? If we add some NH3 into the reaction at equilibrium, all right? Le Chatelier's principle says whatever we do to the reaction to perturb it, the reaction is going to try to do the opposite thing. It's going to try and undo what we did.
So isn't it also going to do it to the left because we're making like a gross amount of product?
It's going to shift to the left, and the reason why is because that's the way that we can get rid of that extra NH3.
Yeah.
Right?
Yeah,
We
we're
can
making
lower
more
our amount of
reactants.
NH3 by shifting to the left to turn it back into N2 and H2. So now that we know which direction we're shifting, let's talk about what happens to the pressure of N2 here. If we shift to the left, that means we're making more N2. So our pressure of N2 should go up. If we're shifting to the left, we're getting rid of some NH3, so the pressure of NH3 should go down. Now you guys can tell me the last two. If we're shifting to the left, what should be happening to the pressure of N2 here? Oh wait, we already answered that. Oops. All right, that's a repeat. But what about the pressure of H2? Is it going to go up or going to go down?
Up.
I didn't hear what was said there, sorry.
Up.
I heard up. That makes sense. Shifting to the left means we're making more of each of those reactants. So making more means making more pressure of each of those since they're gases. So let's give it a check. Awesome, that's 2 in a row. So I want to do another example question. I don't like that one. I'm going to use the reaction, but I'm not going to use the question, all right? Okay, I like this one. I like this one a lot. So what I want you to tell me is if we increase the pressure on this reaction, are we going to shift the reaction to the left or to the right? Be prepared with an explanation why.
Wait, you said raising pressure, not temperature?
Yes, we're talking about pressure now. It's just there isn't a good Alex topic for pressure because their question about it was like it assumed that you knew too many things.
Okay.
All right, so we're creating our own question, but we're just using this reaction. All right. So if the pressure goes up, which way does this reaction shift? To the left or to the right? Or does it shift at all? Maybe it doesn't. It does.
My immediate response is it explodes, but when I say that out loud, it doesn't sound right.
Not every time we increase pressure do we get an explosion.
So I'm spitballing here because I don't quite understand the pressure one. I'm spitballing. So if we increase pressure, that would increase the products. So wouldn't it? Because increased pressure means more collisions, then it would be because it has more moles, so it would create the more collisions. Is it something along those lines, or am I in outer space?
There is a line of reasoning in there that has something to do with collisions.
Yeah.
So what I want you to think about is Le Chatelier's principle. All right. So if we increase the pressure and that is our disturbance, what is the reaction going to want to do?
It's going to try and reduce its pressure somehow.
It's going to try and reduce its pressure. Very good. All right. So to me, that's always the easiest place to start with Le Chatelier's principle. Whatever we're doing to disturb the reaction, we know the reaction's going to try and do the opposite. So the natural question that pops into your head based on Le Chatelier's principle is, which direction is this reaction going to shift to be able to decrease its own pressure?
Left.
I said that much like louder and more definitively than I even intended to here. All right. So which way does the reaction shift if we increase the pressure in order to get back to equilibrium?
I would
The
assume
right.
to the right because it's trying to make more reactants that can like leave.
Wait, these are products, not reactants.
Sorry, products.
So, okay, where does pressure come from?
Pressure comes from more collisions within a confined space.
Okay. So if we look at the reactants and the products here, is there a side that has less collisions and a side that has more collisions?
Yes. The right side has more collisions because there's more moles.
So we've increased the pressure, which means we're creating more collisions. The reaction's going to respond by doing the opposite, shifting to make less collisions. Which side do we shift to make less collisions?
Left.
I'm just going to scratch this out and let
I mean, that's pretty much what I said, Dr. Mouse.
But originally, your contention was that we would make more products, and that turned out to not be so accurate.
Yeah, I know.
But you were thinking about collisions, right? The
Yeah.
pressure one is really hard, so make sure that you're taking it back to that first principle, Le Chatelier's principle, that tells us that if we disturb the reaction by making more pressure, in other words, if we disturb the reaction by increasing the number of collisions, the reaction's going to try and shift to make less collisions. We know that whichever side has less moles of gas, there are 2 moles of gases on the left, there are a total of 4 moles of gases on the right. Shifting to the side with less moles of gas makes less collisions. So that's how this reaction can lower its pressure. It can shift to the side with less moles of gas. Pretty awesome. Okay, What about this reaction? If we decrease our pressure, which direction is that going to shift our equilibrium? All right, if we decrease the pressure, if that's our disturbance, which direction are
one's
we
not
going to
gonna
shift
shift, is it?
our equilibrium?
That's a good question.
I'm just guessing, but I want to say it's to the left.
But I don't want guesses. I want analysis. All right. So
My
let's-
analysis is that there's going to be more moles of gas on the left, and so there's because no, I'm sorry, that's wrong. Let me rephrase. Because we're decreasing the pressure, it's going to look for where there's less collisions, and there's going to be less on the left, and that's where it wants to go because it wants to cause more collisions. That's my rambling guess.
Sarah, how many
Okay.
moles of gas are there on the left?
Oh,
Two.
you know what? Never mind. Let me take that back.
It's gonna stay the same.
How
There's
many
only
moles of
2
gas?
and 2.
2 and 2, right? So 2 moles of gas on each side. So
Why'd you trick me?
because there might be a trick coming up on the exam, and I don't want you to be fooled there when there's a grade attached to it.
Cough, hint, cough.
This is called formative assessment for a reason. We are stealing our wits in preparation for summative assessment. All right, so where you demonstrate the your knowledge for a grade. So this is just practice, but it's important practice. So the analysis here is, if we decrease the pressure, the reaction's going to want to increase its pressure, right? So it should shift toward the side with more moles of gas. There are 2 moles of gas on the left, and oh crap, there are also 2 moles of gas on the right. That means this reaction can't do anything about a change in pressure, so the equilibrium is unaffected.
But my reasoning was right. That was just wrong about the moles of gas.
It is based on the number of moles of gas, right? But you got to count those and be accurate with that count. Okay, so hopefully now that you guys have had a day to like mull over Le Chatelier's principle, this is starting to become less of a thing to be scared of. Any more questions? Are you guys feeling more comfortable with Le Chatelier's principle?
Heck yeah, I'll slay it in battle. I'm done.
Okay,
I'm
Kat,
sorry.
good for you.
Hey, if you need help, I can help. You know
Yes,
I'm-
please, please, please. After class, you, me, help, please.
Hi.
Thank you.
I also want to call your attention to a short video that I posted today as an announcement.
Such a good video.
It is.
I
It's
have
really
not
great.
seen it
It's
yet,
like
but I saw the announcement.
I can't do Le Chatelier's principle in 5 minutes, but Professor Dave apparently can. Never met Professor Dave, but he's got long hair like me and is much more succinct in explaining Le Chatelier's principle. Now, it doesn't cover tons of examples, but there's a little pictorial guide to how the balance shifts in every case, and it's really worth it. So if you're still struggling, those 5 minutes will be 5 minutes well spent. You should definitely check that out.
And it has already been added to my YouTube queue. Got it.
Good. Yeah, it's pretty awesome little video. I really liked that one a lot. And I'm definitely not haughty enough to think that only my way of explaining Le Chatelier's principle is the correct way. I just want you guys to understand it. And I realized that it's not an easy thing to understand, right? So it took me a long time to get comfortable with Le Chatelier as well.
Dr. Mas.
Yeah, who was that?
Anna.
Yeah, speaking
Anna,
of
what can I
video,
do?
I was looking at your video for chapter 7.7. It's not working.
7.7.
The intermolecular forces video.
What the butt? Hold on, let me look for just a second, okay? Let me see if it's an everybody thing or if it's just a temporary you thing.
How about we just don't do that?
No, we have to learn about intermolecular forces. What? We only have one more chapter to cover, and we have
That
like
was so good.
I was
there's
gonna
so
say,
much time.
I'm okay with it if we don't do it.
No, we got to do it. We got to do it.
We should just remove that portion from the test then. We can do
Hey,
it.
Dr. Musk,
Portion
remember
from
when
the
you
test.
said, why are we in this class if we are not going for an exam? We're just shooting the crap about chemistry.
Right. So yeah, chapter 7.7 is going to be on the exam. Anna, I'm not getting it either, so I'll repost that link. It's probably a link problem, so I'll search through my library and find it again. Okay.
All right. Thank you.
You're welcome. That's so lame. What the heck, YouTube?
What?
Why did my link die? I don't like that. I loved that video. Oh, that makes me so mad. Maybe I'll have to record it again, which is also fine because I love talking about intermolecular forces. It's one of my favorite things.
Okay. I'm nosy now. What's your top 3 favorite things to talk about as a chemistry teacher?
Probably number one, and this may be no surprise to you, I love talking about anything to do with Lewis structures. So Lewis structures are so fundamental to our understanding of organic chemistry specifically that everything to do with those. So not just Lewis structures, but Lewis structures, bond angles, shape, polarity. There's so much in the behavior of covalent molecules that's wrapped up in just like what their three-dimensional structure is, that if you understand that well, it makes a lot of things easier, including intermolecular forces.
Good to know.
So yeah. So if you thought that learning about shape and polarity weren't important, well, they're coming back to bite you now. We can never really get rid of anything in our brains in this class. That's why I don't feel like we have to have a comprehensive final exam, because really, like, if you didn't understand shape and polarity, then you're going to end up not understanding intermolecular forces either. So if you didn't understand stoichiometry math, then you're probably not going to be able to do calculations with concentration either. So it builds. It's like a scaffold, right? So if you lose one floor of your elevator, then your tower gets really wobbly quickly. Let me reshare my screen. So I wanted to begin our discussion of chapter 7 tonight. And we are going to talk about the individual gas laws. You will need to remember those, but in reality, when we use the gas laws to discuss gas behavior, the ideal gas law combines all of those individual gas laws. All right. So I'm going to leave the topical videos to teach you about those individual gas laws. Boyle's law and Charles' law and Avogadro's law are the only ones that we'll really focus on. There's also one called Amonton's law that relates pressure and temperature, but we don't really need that law to establish all the relationships we need to get to the ideal gas law. So let's do a quick review of the individual gas laws, and then we'll get to the ideal gas law. Yeah, there's my unavailable video. That's lame sauce. And I will fix that tonight. That makes me so mad. Or I'll probably just record something new because I'm in the mood to talk about intermolecular forces now.
Nerd.
Ouch. Very ouch.
Bro.
Not an ouch. I'm a nerd. Have you seen my gaming setup?
Okay, so quick recap on the individual gas laws. Boyle's law tells us that as the pressure on a gas increases, the gas volume decreases. So pressure and volume have an inverse relationship. Now, mathematically, we sometimes say it like this. Pressure is proportional to 1 over volume. Or we can say pressure is equal to some arbitrary constant over volume. All right, C is just a constant. Charles' law tells us that as the temperature of a gas increases, the volume of the gas increases. Now we're leaving out some like lawyer speak here, all right? So this statement is only true if a couple of other things don't change at all. So how could we establish a relationship between pressure and volume if we also had temperature changing at the same time? How could we establish a relationship between pressure and volume if we were changing how many moles of gas were in our container at the same time? So the only way that Boyle's law can be true is if we have a constant number of moles of gas and a constant temperature. All right, now you know all four variables that we have to worry about when we're worrying about the behavior of gases: pressure, volume, number of moles, and temperature. So for Charles' law, temperature and volume are the two that we're messing with. So which two are we not messing with? Which two should be constant if we're talking about Charles' law?
Pressure and moles.
That's right. The pressure and the number of moles of gas have to remain constant for Charles' law to be true all by itself. All right. I just misspelled Avogadro's name. Avogadro's law. Now, where did Avogadro show up early in our class?
Avogadro's number.
Which told us what?
How many pieces are in a mole of anything?
Yeah, so Avogadro is synonymous with the concept of the mole. Avogadro's law is relating moles of gas to volume. Also, this may be the most lame sauce law in the history of chemical laws, because just think about the statement that we're making and how absolutely elementary it is. If we put more moles of gas into a balloon, what happens to the volume of the balloon?
Gets bigger.
Yeah, right? So Avogadro's law literally tells us if we blow up a balloon, the volume goes up. That's what Avogadro's law tells us. When we put more moles of gas into a container with a not fixed volume, the volume increases, right? More moles of gas mean greater volume. So what things can't we change if we're worried about moles and volume?
The pressure and the temperature.
Very good. So these three laws are really the only ones that we need to derive the ideal gas law. If you're worried about Amonton's law, It relates temperature and pressure of gases. So as gas temperature goes up, the pressure also goes up. So think about us having a pop can that has headspace above it that has pressurized CO2. If you have that pop can in a really, really cold container and you pull it out and squeeze it, you might be able to squeeze that thing a little bit because the gas part of that container isn't that pressurized. Try and do the same thing at some point. If that container has been sitting out in the warm sun for a while, it will feel rock hard because the pressure of the gas in that container is much, much higher at a higher temperature. That only works if we're operating at constant volume and a constant number of moles of gas. Really, these first three laws are the laws that I teach all the time because those are all that you really need to be able to develop the relationships everywhere else. So even though Amonton was the first one to look at the relationship between temperature and pressure, we can already infer that relationship by having these other relationships straight. So if we combine all of those gas laws, we get this succinct little equation. Oh, let's talk about the mathematical version of each one of these. So as the temperature of the gas goes up, gas volume goes up. In other words, temperature and volume are directly proportional to one another. So we could say something like this: temperature is equal to a constant times the volume, or temperature is directly proportional to volume. Either one of those would be fine. For Avogadro's law, we can say that number of moles is directly proportional to volume, or that number of moles is equal to some arbitrary constant times the volume. And then for temperature and pressure having a direct relationship, we can say that temperature is directly proportional to pressure, or we can say that temperature is equal to some arbitrary constant times pressure. So what I want to look at now is the ideal gas law. The ideal gas law contains all of those relationships summarized in a pretty easy to remember little equation. PV equals N RT. So look for each one of those individual gas laws. I'm going to have to zoom out so you can see all of the individual gas laws.
Wait, where's the R from?
R is the constant. Note that in the mathematical version of each of these, we had some proportionality constant, all right? Now that constant is only there because pressure and volume, or pressure and 1 over volume, they don't have the same units as one another. So that constant has to be there in order to cancel unlike units out. And it turns out that that constant, the ideal gas constant, the reason it's in there is just to make all of the other units that are in that constant cancel one another out. It's called a proportionality constant for that reason.
Do you know why it's an R and not a C?
I didn't write it.
I was just wondering.
I don't know. I will say that that is a more or less universal letter. Remember how some books have KEQ and some have K sub C for equilibrium constants? Every book has R in that spot.
Huh.
So there must have been a good reason to use that letter originally because it's stuck really hard. Nobody has tried to branch away from that.
Okay.
That's not really an answer because I don't know what the reason for them choosing R is, but I know that everybody uses it. And it could just be that there's no really strong reason to not use it, so people have just accepted it. We always think that there's some sort of underlying philosophy with our choices in the world of chemistry. It could just be that the first paper that summarized the ideal gas law used R, and everybody was like, all right, that's fine, whatever. So let's take a look at the relationship between pressure and volume here. Well, it looks like if N and T are constants, then nRT, that whole side of the equation, is a constant if N and T are constants because R is a constant. So if we're looking at Boyle's law, what we see by making this side of the equation a constant is that pressure times volume is a constant. Does that summarize Boyle's law well for us? If this is a constant, what has to happen if we increase our pressure? What happens to the volume? If P times V is a constant and P goes up, what has to happen to V?
V goes down.
Goes up.
Oh, I heard both things. I heard goes up and goes down.
It goes down because Boyle's law says if pressure goes up, volume goes down.
So let's say that P times V is 1, all right? And we could get there by having our pressure be 1 and our volume be 1, and then our constant would equal 1. What if we raise our pressure to 2? If the other side of the equation is a constant, then our volume would have to go down in order to make the two sides of the equation equal, right? So pressure and volume have to have an inverse relationship with one another if pressure times volume is a constant. In other words, that relationship between pressure and volume is maintained in the ideal gas law, all right? All of the other individual gas laws, all those relationships are maintained in this equation, which makes it really easy because then we don't have to memorize all of these other than if we're in a chemistry class to remember whose name is attached to each one of the parts of the ideal gas law. You should know Boyle's and Charles and Avogadro's laws, but in reality, when we use them as part of the ideal gas law, all right? It's just these scientists dedicated their lives to uncovering these parts of the ideal gas law. So it feels a little cheap to just like throw those names away completely and forget about them and just say, well, now we know all the relationships. We'll just call it the ideal gas law. Not really fair to them. If I had spent my entire life trying to come up with a cure for some disease, and then my cure was the cure that they settled on for a host of diseases, and it got named something else because I only had the one disease in mind when I cured it, I would be kind of irritated at them not mentioning my name. I don't know. Maybe that's like, I'm sure that Boyle and Charles and Avogadro don't care anymore because they're all dead. But still, it's important that we recognize their contributions. So let's focus a little bit more on the ideal gas law. Make sure we understand what each of the variables is talking about and what units we expect to see when we see those variables. Key is pressure. And even though we're starting off with pressure, it's actually the place that we can end up having the most issues in terms of units, because the pressure in the ideal gas law can be any one of a number of different units. There are lots of different pressure units that are in common use. All right, so this isn't one that we use very often in the world of chemistry, although some chemists do use it. You guys have probably heard of this unit before, PSI. Anybody know
Pressure
what that
per
is?
square inch.
Yeah, pounds per square inch, right? That's a unit of pressure that we use to talk about how inflated our car tires are. All right, the units of pressure that we use in the world of chemistry, the most often anyway, are pressure units of atmospheres, which are abbreviated as ATMs. Or these two units that are actually two different names for the same unit, torr, or millimeters of mercury. So these are the units that we'll focus on in here, but in reality, in the ideal gas law, we can use any unit of pressure we want to. The only thing that changes is when our unit of pressure changes, the value of the ideal gas constant has to change too to go along with that pressure unit. So we'll talk about what that means in a second. Now, I will give you the way to convert between these two pressure scales, all right? So we can convert between atmospheres and torr because one atmosphere is exactly the same size as 760 torr. And I probably should give 3 sig figs both places. All right, there we go. That's much better. So if we have a pressure in units of torr, we can use this as a conversion factor to convert it to a pressure in atmospheres. For example, if I have a pressure of 3.38 atmospheres, what's my pressure in torr? Here's your conversion factor. If you thought you could get away from using conversion factors because we're all the way in chapter 7,
Okay, I got an answer with 4 sig figs.
It's
Does that mean you can't round it to 3 sig figs?
570.
Shouldn't our conversion factor look like this to get rid of our ATM units and end up with torr units?
Yeah.
Yeah. And we know that there are 760 of those torrs in every one of our ATMs.
So shouldn't it be 2,570 in 3 significant figures?
So my calculator is giving me 2,568.8. How do we round that to 3 significant figures?
2.57
Oh, I
times
like
10
that.
to
We
the
can use scientific notation. I'm a big fan of that. Oh, whoops. Let's use the right units so we don't get marked off. So 2.57 times 10 to the, oh wait, that's also wrong. So times, no, that's right, times 10 to the third. That will work fine. Or if we wanted to write it without scientific notation, isn't that acceptable as well? There are 3 significant figures in that quantity because remember that our zeros are only significant in numbers that have a decimal point, right? Alex wouldn't like this version of the answer, but do we really care that much what Alex feels about our answer? It wouldn't mark this wrong. It would just be irritated about it. I
want
actually
to find this, Alex.
I like irritating Alex when I can, as long as it doesn't give me a wrong answer at the same time.
I like it when it says correct, but you should have written it this way. And I'm like,
And your retort is, okay, so you're saying it's correct. Moving on.
yeah, pretty much.
Okay, so we know how to convert between pressure units if we ever need to, but you may see atmospheres or torr as your pressure unit in the ideal gas law. A lot of the other units aren't nearly as forgiving, all right? So for volume, we're gonna stick to just liters. Our volume should always be in liters when we're using the ideal gas law. And the reason why is because In all of the versions of the ideal gas constant, the units in there are liters, and we need to make those liters cancel, or else we're not going to cancel all the units in this equation that we need to. There's also not much play in our units representing a number of moles. If N is moles, then the only unit that really works there is moles of gas. Now for temperature, only one unit works as well, and there's a specific reason for this. In order for the ideal gas law to work properly, the temperature scale has to be an absolute temperature scale. In other words, let's say that we're talking about the relationship between temperature and volume, Charles' law, right? On this temperature scale, if our pressure and our number of moles don't change, then doubling our temperature should double our volume at the same time. That only works if the temperature scale is absolute. In other words, there's no negative side to the temperature scale. And only one of our scales is an absolute temperature scale. That's the Kelvin scale. So when we use the ideal gas law, our temperatures are always going to be in Kelvin. Our volumes are always going to be in liters. The only unit that there's play in is the pressure, all right? So let's look at what we would do when we put all of those units in, and we'll just pick a unit for pressure to start with. We'll pick atmospheres. And for volume, we're always going to be in liters, so PV equals N. N is our number of moles of gas. R, we're trying to figure out what the heck is going on with R, so we'll just leave it the way it is. And then for our temperature, our units should be Kelvin. Now I'm just going to do a little bit of algebra and figure out what our units for R have to be, because our units for R have to get all the rest of these units to cancel one another out. So if I divide both sides of this equation by moles, and I end up putting moles in the denominator over here. If I divide both sides of the equation by Kelvin, I end up putting Kelvin in the denominator over here. So it looks like R has to have units of liters times ATM divided by moles divided by kelvins. Now that unit doesn't exactly roll off the tongue, but this is the correct unit for R when our pressure is in atmospheres.
And what is R again? I'm sorry, I'm drawing a blank.
It's the
And I forgot
The constant.
the constant. Oh, okay.
And not only is it a constant, but this is the value of the constant when our pressure units are in atmospheres. You should write that down and have it available anytime you're doing work with the ideal gas law. That is the number that you will put in for R whenever your pressure units are in atmospheres. When our pressure units are in torr or millimeters of mercury, two different names for the same unit, the value of R is different. We end up with a value of 62.4 liter torrs per mole Kelvin. So this constant is the constant that we'll use whenever we're dealing with pressures in units of torr. Wow, that hour went by like greased lightning.
And I'm more confused
Go
at the
grease
end.
lightning.
Why are you more confused? What can I help you with, Kat?
I just don't understand this constant. It's not clicking. It'll click eventually. I know it
It
will.
will. Let's do one example problem and see how we use the constant. And then it's a constant. All we do is plug that in whenever we use the ideal gas law. So if our pressure units are in atmospheres, this is the value for R that we're going to use every time. All right. So let's do an example where we use the ideal gas law to solve something. And then you'll see how we use that R, and it'll be a lot easier. All right, this is a quick one, and we will continue with our discussion of the ideal gas law next week also. All right, we are running out of sessions. We do have 3 sessions next week, and then the week after we can have a couple more sessions as well. We have like 5 more classes that we could have together before we open the 3rd exam. But I mean, that should be plenty for us to get through chapter 7 with flying colors. So if we finish up early, then we can have some time for just a 3rd exam review as well, which seems like it'd be a good idea.
Yeah, that would be great. That'd be wonderful.
Okay.
And a virtual pizza party.
Yes.
As long as I can eat gluten-free pizza.
I mean, I still
Absolutely.
need a sticker.
Absolutely.
I mean, I think I'm owed a sticker from exam 2. A big puffy one. I really am sad we don't have in-class classes because
Mail her a sticker.
I'm not, because I would never be able to be in this class if we were in classes.
why?
Because I'm not on the island. I don't have a car.
Oh, yeah.
If a gas's temperature is 25.0 degrees Celsius, its pressure is 1.35 atmospheres, and there are 4.3 moles of the gas present, what is the gas's volume in liters? How will we solve that? We'll solve
Had to throw in that conversion factor, didn't you?
Which
Yeah, the Celsius to Kelvin.
Oh, that's
So I
easy.
do that
That's
for
the
a
easy
reason,
part of this.
because most of the time when scientists report temperatures, they report them in degrees Celsius. In this one case, we have to convert to Kelvin to use the temperature in the ideal gas law. So I'm modeling based on real world, because we don't go around like your thermometer, even up in Canada where they're evolved enough to use the metric system, their thermometers outside of banks don't give you the Kelvin temperature. They give you the Celsius one, right? So this is a conversion that we have to do all the time when we use the ideal gas law. All right, it looks like our pressure, I'm just plugging in what I know here, is 1.35 atmospheres. Our volume is what we're trying to solve for, so I'm leaving that as a variable. It looks like there are 4.3 moles of gas present. The ideal gas constant, because we're in units of atmospheres, has a value of 0.0821 liter atmospheres per mole Kelvin.
Oh, that's where that goes. Okay.
And then we've got to convert our Celsius temperature to Kelvin.
This is not how Alex did it, but it makes more sense. Okay, okay.
In reality, we know pressure, we know moles, R is a constant, so we know that, and we know temperature. So out of all of these variables, there's only one unknown, volume. So we've plugged everything in, and we can use algebra to solve for what we don't know. We divide both sides by that 1.35 atmospheres. And that should be our final volume that we need to calculate.
My brain hurts so much.
How many significant figures should I be keeping for my volume?
3, 2.
2.
2.
So can you summarize why we keep 2 sig figs? Because you're correct.
Because we go with, because we're multiplying, first of all, and or multiplying or dividing, and there we go with the lowest amount of sig figs in one of the numbers. I'm really butchering this, but
No,
4.3
I said it better myself.
okay, 4.3 has the lowest amount of sig figs, and so it's 2, and so we go with 2.
That's absolutely correct, and exactly the way that I would have explained it as well. Great job.
Okay,
I love it
great.
when other people do my teaching for me. Fantastic. All right, so we round to 2 sig figs, which means 77.9 rounds up to
78
liters. So we just calculated our volume of this gas that we didn't know, because we did know its temperature and pressure and number of moles. That's one of the main ways that we use the ideal gas law. If we know 3 out of those 4 variables, we can use the ideal gas law to solve for the 4th. All right? Kat, is that less scary now than it was a minute ago?
It is. That actually makes a lot more sense than how Alex described it, honestly. So I really wish that is how they would have described it, because I would have gotten through that section a lot faster.
Well, no explanation is perfect. I'm sure that there's a subset of people, like every quarter I get a few comments that are like, the way that Alex describes everything is exactly what I needed to hear. And I think it's so amazing. What a wonderful resource. And then there's everybody else after that as well, right? So no one method is going to reach everybody. So that's why we have to try lots of different things. And hopefully we all find some way of understanding that works for us personally, right?